Hello everyone, I am Anita studying MTech in Embedded System from Vellore Institute of Technology. In this video, we shall learn about what is Hall effect sensor and its principle of working, types of Hall effect sensors, and various applications. What is Hall effect sensor? Hall effect sensor is one kind of a magnetic sensor. It is designed to respond for a wide range of positive and negative magnetic fields. Magnetic sensor whose output signal is a function of magnetic field density around it is called Hall effect sensor. Magnetic sensor is actually a solid state device that are becoming more popular these days because of its ability to sense position and calculate velocity or directional movement. These are a popular choice of an electronic designer these days because they are immune to vibration, dust, and water, and there is a low maintenance cost and its robust design. In automotive system, we will widely use magnetic sensors like in angular position of the crankshaft for the firing angle of spark plugs, the position of the car seats, and seat belts for airbag control or wheel speed detection for the anti-lock braking system. This is a brief discussion about a Hall effect sensor. Now we shall see what is its principle of working. Hall effect sensors are activated by external magnetic field. We know that magnetic field consists of two basic characteristics, that is a flux density and polarity. The output signal from the Hall effect sensor is a function of this magnetic field density around the device. When the magnetic flux density around the sensor exceeds certain preset threshold, the sensor detects it and generates an output voltage called Hall voltage. We can see here the gray color rectangular material. This is a p-type semiconductor. Hall effect sensors basically consist of a thin piece of rectangular p-type semiconductor material. It is basically made of gallium arsenide, indium antimonide, or indium arsenide. This material is passing a continuous current through itself. When the device is placed within a magnetic field, here you can see a magnet. When this device is placed in the magnetic field, the magnetic flux lines exert force on the semiconductor material. Because of this force, which is called as the Lorentz force, the charge carriers, here the electrons and holes, which are going through the semiconductor material, now got deflected. You can see in the image. This moment of charge carriers experience when they are passing through the semiconductor material. As these electrons and holes move sidewards, a potential difference is produced between the two sides of semiconductor material. Then the movement of electrons through the semiconductor material is affected by the external magnetic field. This effect is called Hall effect, which is named after a scientist, Edwin Hall. To create more potential difference, that is, which is intensive, the flux lines must be perpendicular to the flow of current and be of the correct polarity. Generally, we will face it the south pole. Uh, some applications of this Hall effect are, for example, we can find a type of magnetic pole. Whenever we were given a magnet, we can detect what type of magnetic pole and then magnitude of the magnetic field. Like a south pole would cause the device to produce a voltage output while the north pole would have no effect. By this, we can find the type of magnetic pole. Hall effect sensors are switches designed to be on and off. How it is, we can see further. Then here we are given a formula: output voltage VH. This is called the Hall voltage. This basic Hall element is directly proportional to the strength of magnetic field passing through the semiconductor material, that is output proportional to B. This output voltage can be quite small, ranging from only a microvolts. So commercially available Hall effect devices are manufactured with built-in DC amplifiers because the voltage is very small. This also allows the Hall effect sensor to operate over a wide range of power supplies and magnetic field conditions. Here we can see RH I by T multiplied by magnetic flux density. Each of the naming convention is given here. And then we can see the types of Hall effect sensors. There are basically two types of Hall effect sensors. They are linear or analog sensor and a digital sensor. This linear or analog output sensor comprises of, you can see in the figure, it comprises of a voltage regulator, Hall element and high gain amplifier. Till that part it belongs to analog sensor. Then this linear or analog sensor gives us a continuous voltage output. We can see it in the graph here. Hall effect sensor, as the strength of magnetic field increases, the output signal from the amplifier will also increase until it begins to saturate by the limits imposed on it by the power supply. Additional increase in the magnetic field will have no effect on output, but it goes to saturation. This type of analog sensors are mostly used in finding proximity because of continuous linear output. One more type is digital sensor. This digital sensor provides only two states, either on or off. This digital sensor has a Smith trigger in addition. It is basically useful to provide us at two levels. When the magnetic flux passing through the Hall sensor, as we discussed, exceeds a preset value, the output from this device quickly changes between its off condition to on condition without any type of contact bounce. This built-in hysteresis eliminates any oscillation of the output signal as the sensor moves in and out of the magnetic field. So we can say digital sensors have only two states, on and off. This kind of digital sensors are mostly used as switches. We can also call as Hall effect switch. They are often used as limit switches in 3D printers, CNC machines, and for detection and positioning in industrial automation. There are again two types of digital Hall effect sensor. We call as bipolar and unipolar. This is a simple classification. Bipolar sensors require a positive magnetic field to operate them and a negative field to release them, while unipolar sensors require only a single magnetic south pole. Single magnetic south pole can operate and release as they move in and out of the magnetic field. Now, most Hall effect devices cannot directly switch large electric loads as their output drive capabilities are very small. We have seen already the voltage is also in the range of microvolts. So it can draw very small currents in the range of 10 to 20 milliamps only. For large current loads, an open collector NPN transistor is added to the output. This transistor operates in its saturation region as a NPN sink switch which shorts the output terminal to the ground whenever the applied flux density is higher than that of the on-set on preset point. The output switching transistor can either be in an open emitter transistor, open collector transistor configuration, or both, providing a push-pull output type configuration that can sink enough current to directly drive many loads. This can be used uh, including relays, motors, LEDs, and lamps. Now we have seen all this, what is Hall effect, what is its working principle, types of Hall effect, and we can see some of the applications. Uh, Mostly Hall effect sensors in automotive industries are used as a wheel speed sensors or crankshaft or camshaft position sensors, Hall effect switches, MEMS compasses, or proximity sensors. We can see first as a wheel speed sensor how it calculates the speed of the wheel, which is RPM. We can see here this sensor is having a Hall element, which is here Hall effect sensor, and then a permanent magnet. We can see that is placed near the tooth disc attached to the shaft, and there is a gap between sensor and the tooth disc. This gap is very small, so when every time the tooth is passing through the sensor, that is when the disc is rotating, sometimes we'll get a lesser gap and sometimes we'll get more gap because of this change in the surrounding magnetic field, which causes the output sensor goes through high or low. Then uh, it creates a voltage in the form of on and off, like a square wave, which we have discussed earlier. This square wave is, we can very easily find out RPM. Next, some of the applications are head-on detection, sideways detection, positional detector. This head-on detection, as the name implies, requires that the magnetic field is perpendicular to the Hall effect sensing device and that for detection it approaches the sensor straight on towards the active phase. A sort of head-on approach. This head-on approach generates an output signal VH, which in the linear devices represent the strength of the magnetic field as a function distance away from the Hall effect sensor. The nearer it is, then the stronger will be the magnetic field and the greater the output voltage, and vice versa. Next we can see sideways detection. Second sensing configuration is sideways detection. This requires moving the magnet across the face of the Hall effect element in a sideway motion. We have indicated here with a blue line. Sideways or slide by detection is useful for detecting the presence of magnetic field as it moves across the face of the Hall element with a fixed air gap distance. Depending upon the position of magnetic field as it passes by zero field center line of the sensor, a linear output voltage representing both positive and negative output can be produced. This allows the directional movement detection, which can be vertical or as well as horizontal. So like this, there are various applications of Hall effect sensors. We can see positional detector also. Here, this head-on positional detector will be off when there is a magnetic field present. When permanent magnet's south pole, here indicated with the blue color, is moved perpendicularly towards the active area of the Hall effect sensor, the crossed mark is Hall effect sensor, the device turns on. When this magnet is moved perpendicularly, the device turns on and the lights, the LED. Once switched on, the Hall effect sensor stays on. To turn the device and therefore the LED off, the magnetic field must be reduced to below the release point for unipolar sensor or exposed to a magnetic north pole. To make this LED off, we have to face it north, or we have to reduce the magnetic field. The LED can be replaced with a large power transistor if the output of the Hall effect sensor is required to switch large current loads as we required. So we have understood basic applications of Hall effect sensor, and thank you.